All right, y'all. Today we're going to be talking about finding limits algebraically. So last class we really explored limits graphically. Today we're going to talk them a little bit more in depth from an algebraic perspective. So a couple of things we want to talk about. Okay, the first one is the limit of a constant. So if I have some constant a and I'm trying to find the limit as x approaches some constant c, if all I have is a number, I don't have any x value to plug into, so my limit is just equal to a. And you can just ignore that little extra equal sign we got there. Okay, so limit of a constant just equal to whatever it is because we don't have any x value to plug into. If I have a function, limit as x approaches c of f of x, just like we talked about last class, first thing we're going to do is we're going to plug that c value in and hopefully get out a y value. Plug the number in, get a number out. Last but not least, the limit of our quotient, limit as x approaches c of f of x over g of x, we would plug that value c into all the x's in our function, provided that when we plug it in, that whatever is on the bottom doesn't equal 0. If it equals 0, we're going to have to do that little extra work that we did last class where we might have to simplify or do something else. So let's look at some examples. So I have the limit as x approaches c of 7. So 7, there's no x value, there's nothing I can plug in, so this one is just equal to 7. Okay, so anytime it's just a constant, my limit, no matter what c value, no matter what x value I'm approaching, is always equal to 7. Okay, number 2, we have the limit as x approaches 3 of x plus 4. So I just plug in my function value, so 3 plus 4, which would be equal to 7. Relatively straightforward. Okay, number 3, we have the limit as x approaches 3 of negative 5x. So once again, I plug in that x value, so negative 5 parentheses 3 would be equal to negative 15. And then number 4, I have the limit as x approaches 3 of 5x squared. So once again, I'm going to plug in that x value, so 5 parentheses 3 squared, which is equal to 5 times 9, which is equal to 45. Okay, so relatively straightforward. I'm going to let you go ahead and try 5, 6, 7, and 8 real quick on your own. So go ahead and pause me for right now, and then we'll come back to it here in a second. All right, also a couple ones for us to go over here. So number 5, limit as x approaches c of just x. So even though c is not an actual number, it is still representative of a constant, so I can just plug it into x, and I get out just c. That one might have been a little bit tricky, but not too terrible. Okay, number 6, limit as x approaches 2 of x minus 5, plug in 2. 2 minus 5 is equal to negative 3. Number 7, limit as x approaches 6 of x over 2, so plug in 6. 6 divided by 2 is 3. And then, of course, number 8, probably the most labor-intensive in terms of the math, but I got all those different x's, so I plug 2 in for all of them. Working on all the math, you should get down to 10. So limits algebraically can actually be relatively straightforward if you don't have any of those little extra things like dividing by 0 or something like that. Okay, so let's look at some other examples, and this one's very similar to the one that we did last class. These are what we call indeterminate limits. So when the limit is equal to 0 divided by 0, we want to factor and cancel where applicable. Then we're going to use direct substitution to try and evaluate the limit again. So number 9, we have the limit as x approaches 3 of x squared minus 9 over x minus 3. So we're going to plug in 3. So we get 3 squared minus 9 over 3 minus 3, which is equal to 9 minus 9 over 3 minus 3, which would be equal to 0 over 0, which is no good. That is our indeterminate result. Okay, so that means we have to come over here, and we're going to see if we can factor and cancel anything. So we can factor x squared minus 9 into x plus 3x minus 3. And then we still have x minus 3 on the bottom. Then because I have x minus 3 and x minus 3 on top of each other, I'm going to get those to cancel out. So that gives us the new simplified limit as x approaches 3 of x plus 3. So then I can go ahead and plug in again. So this is equal to 3 plus 3, which is equal to 6. So just to clarify once again, kind of the difference between the limit and the function value. If I was just asked what's the value of the function at 3, the value of the function is undefined because we got that indeterminate result. We actually have a hole occurring at our x value of 3. But our limit, we can go and we can actually do a little bit of simplifying. We can cancel out and we can plug in again, and we can get the value that the function would have gotten to if it wasn't undefined. That's that advantage of limits. Okay. So our last one is number 10. So for number 10, we're evaluating one-side limits algebraically. So one-side limits, remember, we're considering just approaching from the left or just approaching from the right. So we want to know what's going on at the function at that value of 1, even though we might not actually have 1 in the function, we might not be able to plug in 1. Various different things could kind of be limiting us from plugging in that actual value of 1. So in number 10, we have 2 minus x for x values that are less than 1, and we have 2x minus x squared for x values that are greater than 1. So notice we don't actually have 1 in our function. So I'm going to try and find the limit from the left and the limit from the right and use that to find my overall limit. So to find the limit from the left, I'm going to start by plugging in a number just to the left of 1. And a really great number just to the left of 1 would be 0. Now you might be asking, well, Mr. Arbone, I have 2 different functions to plug into. Well, I'm going to also pay attention to the domain, and I notice that 2 minus x is my function that's for values of x that are less than 1. So that means it's for my values of 1, or my values of x that are to the left of 1. So if I'm approaching from the left, that's the function I'm going to use. So I'm going to plug in 0 first. So plugging in 0, I would get 2, wrong color. Plugging in 0, I would get 2 minus 0. 2 minus 0 would be equal to 2. Okay, I'm going to go a little bit closer to see if I can get a better idea of what's happening with my function at 1. Okay, so I'm going to go ahead and plug in 0.5. So 2 minus 0.5 is equal to 1.5. Okay, let's go a little bit closer to see if we can get an even better idea of what's happening. So I'm going to plug in 0.9. So 2 minus 0.9 is equal to 1.1. Okay, just because I want to see if I can get even closer, let's do something a little closer than 0.9, like 0.99. So 2 minus 0.99 would be equal to 1.01. Okay, so hopefully that kind of starts to paint a picture of what y value we look like we're getting to as we get closer and closer to that 1. Okay, let's go ahead and let's do it from the other side. So my right-sided limit for x values approaching 1 from the right side, I'm going to use my second function because 2x minus x squared is existent for x values that are greater than 1. Okay, so I'm going to use my other function, and I'm going to plug in values that are to the right of 1. So let's start with 2. So plugging in 2, we would have 2 times 2 minus 2 squared. So 2 times 2 is equal to 4 minus 2 squared is 4, which would be equal to 0. So let's go a little bit closer to see if we can get a better idea of what's happening. So let's do 1.5. So 2 times 1.5 minus 1.5 squared. That would be equal to 3 minus 2.25, which would be equal to 0.75. Let's get a little bit closer. So if I did 2 times 1.1 minus 1.1, that would give me 2.2 minus 1.1 times 1.1 would be 1.21, which would give me 0.99. Okay, so hopefully, just from doing that, you can probably start to see. So from the right side, I've gone all the way to 0.99. From the left side, I've gone all the way to 1.01. So my left side limit and my right side limit look like they're going to end up getting to a y value of 1. And if I wanted to test that just to be sure, I can actually plug that y value or that x value of 1 into both and just see, even though my functions don't technically get there, what would they equal if I plug in 1? So plugging in 1 real quick, that would be 2 minus 1, which is equal to 1. And plugging in 1 on the other side, that would be 2 times 1 minus 1 squared. And my pen is not cooperating very well, which would be equal to 2 minus 1, which is equal to 1. So we can see that both our left side would equal 1 and our right side would equal 1, which are equal to each other, which does help to corroborate our value of 1 that we got for our overall limit. So one-side limits sometimes can be a little more complicated to think about, but they're really similar to our overall limits. We can still plug those values in to see what's going on and see what's happening algebraically at that function. But sometimes, some of you might have been like, well, Mr. Arbone, if I had a graph, I could have told you this within 5 seconds. And that's true. Sometimes being able to evaluate a limit graphically is a little bit easier, while sometimes being able to evaluate it algebraically can be a little simpler. There's advantages to both. Okay, so that should close up algebraic limits. If you have any other questions, please feel free to ask them in class, and go ahead and start working on that homework.